right, before we set you loose, we'd like to walk through a case study. And the reason here is while the way that we formulated the least squares estimates using the notation of linear algebra and results that you may have seen in your linear algebra class, what we get out of it is actually quite concrete in terms of the sorts of models that we can fit and the way that they can be helpful in describing the world. So we're going to walk through now a case study that has to do with the question, what determines the price of a meal in New York City? All right, so that's a very broad question. In order to answer it, I'm going to put a finer point on it, answer a more specific question, and that is, what determines the price of dinner at an Italian restaurant in Manhattan? And I'm interested in this question, and admittedly, it's also guided by the fact that this is the sort of data that I have access to, so I could answer this question. So let me tell you a bit about the data here. The data come from a company called Zagat. If you're not familiar with it, Zagat is quite a bit like Yelp, but instead of amateurs providing their reviews, Zagat actually sends out professional, trained reviewers, and they review using a kind of a common set of criteria every time. So we can see here they went to a restaurant called Maria, and they have some summary text, which you could imagine parsing and pulling out some interesting information. We see for this particular restaurant that you should prepare to be thrilled, that's brilliantly executed, lovely and refined, gracious and on cue, but they tell you to dress pretty as well and bring your bank manager. And we see this reflected in the numerical data that they're actually, numerical scores that they're also providing. We see four numerical pieces of data that are collected there. One is the food score, the decor score, and the service score, and then we see the cost. So those first three scores, those are scores numbers between 1 and 30, 30 being the maximum possible points. And then the cost is the average price of a meal for a single diner. So we can see this is a pricey restaurant, but it's very good food, a food rating of 27 out of 30. Okay, so this is the sort of data that we have to answer this question. So let's go ahead and look at what it looks like kind of as a data frame, and we see something like this. So, something that we should always be thinking about is going back to notions of granularity and be sure we understand what does every row in this data frame refer to. And in this case, we're thinking about an individual restaurant. It's not surprising. So, for example, this first row is all data on Daniele Ristorante. We should also ask questions like, what shape is it here? What are its dimensions? And we have, in this case, there's 168 restaurants that we have access to. And then we have, in this way that I've shown the data frame, we have 5 columns. Since we're not yet thinking about this in terms of a model, I'm just going to use D instead of P. And note that I'm, counting in D that restaurant of names. I'm thinking about that as data. And in some phrasings, that makes sense to think about row names as data, other times not. All right, the other really important thing that we keep in mind is that we go back to this notion of how's our data collected and notions of sampling. And you have to ask yourself, okay, so these are Italian restaurants in Manhattan, and we've recorded 168. Do you think that this is a sample or a census? Said another way, are there more than 168 Italian restaurants in Manhattan? If you visited Manhattan, you realize that is a massive, massive place, very dense, lots going on, lots of Italian restaurants. This is probably not a census. There are more than 168 Italian restaurants in Manhattan. So, okay, we know that we're dealing with a sample, and we should ask ourselves, is it going to be a representative sample? Well, in this case, we don't quite know enough. We should look more into the way that Zagat chooses which restaurants to survey. My suspicion is that they tend to survey finer restaurants, so a bit pricier. So it could be that any conclusion that we come to looking at this data might not actually generalize very well to all restaurants because we have a non-representative sample. It's possible we might have some bias in our resulting parameter estimates. Just something to keep in mind. Okay, so let's think about how we're going to answer that question. Let's start with a really simple model. Simple linear model. Okay, so what we're going to try to do here is we're going to try to predict the price based on a simple function of food, and it's going to be a linear function. So just two parameters. All right, so this is how we introduce the simple linear model. By now you should be comfortable also with the matrix formulation that thinks about it more like this. So we're thinking about y and theta as vectors, or sorry, y hat and theta as vectors, and x now as a matrix. Y is n by 1, x is n by p plus 1, in this case p is just 1, so we have 2 rows in x, and then theta is 2 by 1. And just a note about x is, always keep in mind that if we're fitting that intercept, that theta naught, then that first column in the x matrix will be all 1s. And one reason that we use this nice matrix formulation is as we start kind of increasing n, increasing p, this is a really nice container for keeping all of our data in a form that we can compute on it very rapidly, but also that expresses compactly what we're doing mathematically. So you can imagine if we're trying to spool this out into sums, once we get into high dimensions, it gets really ungainly, but it stays nice and compact when we think about it as linear algebra. Okay, so this is the model that we're going to try to fit. We saw that we can come up with our least squares estimate of now the vector theta hat using this formulation. And the important thing to note about this formulation is that if you look at everything on the right side here, it's just the matrix x and the vector y. Both of those things are in your data set. So this is just saying take your data, do some operations on it. These are operations that we can do quite quickly, and you'll come out with a vector that are your least squares estimates. So it's a really kind of elegant, compact form for coming up with this particular model estimates. All right, so if we look at this actual data plotted as a scatter plot, now I've made a scatter plot that has the food scores of these 168 restaurants on the x-axis, their price on the y-axis, and we can see that clear linear trend going upwards, that as you increase the quality of the food, the price was increasing correspondingly. It's actually remarkably linear in my book. Something else that we should note here, maybe two features that's interesting about this data set. One is we notice this vertical banding, and think for a moment about the data collection process here. They're scoring these restaurants points between 1 and 30, and in this case it's clear that there are probably no fractional points, that we're just hopping from one integer to the next. So that explains kind of these vertical rows. You might also detect a bit of change in the color of each of those points. That's because I've added some opacity, because we have some overplotting. This is often the case when you're binning continuous data, because you're taking an integer instead of more finer precision, is you have multiple values, multiple observations that have the same values. So you want to be sure to kind of separate them visually. Note that anytime that you fit a model, you don't really have to worry about it. It'll take that into account automatically. All right, so we fit that line. We use the matrix operations to get this, and we come out with these two estimates. And the kind of the one of interest is that second one, the slope. So what does this slope tell us? Well, this model, if we're using it descriptively, it's telling us that, okay, restaurants with one additional point in the food score are associated with a price that is $2.9, $2.90 higher on average. And that's, that it's positive is not surprising. The particular magnitude might be somewhat surprising. What we get once we've come up with these two estimates is we also have now a model that we can use to make predictions. And there are lots of ways that you can measure how good your model is doing at prediction. Just to pull one off here, the R squared for this model is 0.39, and that tells us that of all the variability that we see in our response, the y variable price, that we can explain away about 40%, 39% of it, using this linear model that just takes this information on food. Okay, so we've described the phenomenon of what explains the price in food in New York, the price of dinner in New York at Italian restaurants, and food is part of it, the quality of the food, at least as quantified by Zagat. But what about the impact of other features of the restaurant? So let's fit a multiple regression model. a multiple regression model, if we're thinking about it in a descriptive capacity, it allows us to ask these more nuanced questions. In this case, I'm interested in the effect both of food and of decor on the price. So if we look at the matrix formulation, now all that we've done is added another column to our X matrix. Now we have 3 columns, the ones, the column for food, the column for decor, and as a result, we're going to be estimating a third parameter, theta 2. And we're going to use the exact same estimating equations as before. When we do that, if we want to visualize this, well, we can no longer use a normal scatter plot because this is not just one X, we have 2 X's. So let's actually kind of pop that out and think about a 3-dimensional scatter plot and what the resulting structure should be. So if we're going to make a 3-dimensional scatter plot, we're going to talk about clouds in space. If we're thinking about the shape of our model here, a simple regression model with a slope and an intercept, that was making a line in 2-dimensional space. So if we're thinking about this model, a 3-dimensional cloud, think for a moment about what shape that should be, what shape the model should be through that cloud of points. Okay, maybe at this point you have a sense that really what it should be is a plane. So let me just play with this a bit, give you a tour. This is using a piece of software called Plotly. It is extremely powerful, extremely cool, both for static graphics, but particularly for graphics like this, that are interactive graphics. If you're curious about it, Professor Gonzalez has posted a notebook where he walks, a video where he goes through some Plotly code and its functionality. It's really fun to play with. So here we see the 3-dimensional data cloud, and our 2 axes here on the X, we can see food, we can see decor, our 2 X's, and then we can see the plane that we're drawing through it as it's going up to predict price. It's this plane that slices through. And you know, if you think about, we were looking at loss functions before, these loss functions that define our model. In this case, we're thinking about a loss function that's in 3 dimensions. And every different value of at least theta 1 and theta 2 is going to result in a plane that's tilted slightly differently. And this is the particular tilts that result in the lowest overall mean squared error. Okay, so that is our new 3-dimensional model. So let's look at our actual estimates. Our least squares estimates here, now we have 3 of them. We have the intercept, we have theta 1 hat, which is the intercept for the slope for food, the coefficient in front of food, and then we also have the coefficient in front of decor. Now, notice actually that theta naught and theta 1 have changed a bit. So theta 1 previously was 2.9, and now it's 1.6. Now let's focus on interpreting that 1.6, thinking about it from a descriptive capacity, and we'd say something like this, that for 2 restaurants with the same decor, the one with an additional point in food is associated with a price that is $1.60 higher on average. Notice, really importantly, that first statement, for 2 restaurants with the same value of decor. Or you could also say controlling for decor. Because the fact of the matter is, you know, that 1.6, that doesn't hold constant as the thing that relates the food to the price, unless you don't change the value of decor. Said another way, if you're looking at this tilted line here, you know, what you need to do is you can't just compare any 2 restaurants that differ on food. You need to fix the decor. So you need to draw a vertical plane here, say along decor is 15. Now you're only comparing restaurants with a decor of 15. And then if you look at the slope of that line there, it'd be telling you that, right, each time you augment food by 1, the predicted price is going up by 1.6. So in a way that makes it more complicated, but it's more of a feature than a bug, because it allows us to say that, you know, we really are just interested in the effect of food after we've already controlled for decor. What extra, you know, impact does food have? And that's what this is telling us. It also is going to be improving our predictions. So we talked about last lecture how if you increase the number of features in your model, it actually can't decrease the R-squared value. It can only stay the same or increase. We've actually gone up from 0.39 to 0.62. Now, kind of to get a sense of why that's true, let's actually look at both of these models on the same scatter plot. So what I've done here, the one on the left here, this is the one that we were just looking at. This is fitting a multiple linear regression model where we're estimating 1.6 and 1.8 for our two slopes. That's kind of describing the tilt of this plane. Now I could go back and take that same three-dimensional scatter plot, but still only express as a plane that that one model, and what we get is, sorry, the simple model, and what we get is this. So notice that we still have a tilted plane, but it's only tilted in one direction. It's only tilted, if we look here, we see that there's no slope, but if we look at it in this dimension, we do see some slope. So kind of what this is telling us is that if we think back to why models can only increase their R-squared when we add extra dimensions, think about this where we had two dimensions. That plot on the left, that plane can really tilt in two dimensions to find the particular plane that threads through the points in the way that lowers the mean squared error maximally. Now, we're giving it as one of its options this model here. So one of these tilts is the one where theta 2 hat is set to 0. Now it turns out that that one actually doesn't have a lower mean squared error than this one where we set theta 2 to 1.8. So since that's non-zero, we know that we must have decreased the mean squared error a bit, increased the R-squared. All right, so let's, thinking about these two models, it kind of brings up another more informal definition that we can use for what is a model, and that is not just a useful simplification of reality. I think that's our most robust definition, but if we're thinking about models for their descriptive capacities, another definition that's really useful to think about is you can think about a model as a specific answer to a specific question, or rather, once you are looking at your estimates, you're looking at a specific answer to a specific question. Let's look at the questions that correspond to each of these models. The first question really that we asked and then answered was, what is the relationship between the quality of the food and the price at Italian restaurants in Manhattan? And we answered that question with this model by looking at the coefficient in front of food. Now, if we're interested in something slightly different, if we're interested in, all right, I'd like to control for the quality of the decor, now what is the relationship between the quality of the food and the price at Italian restaurants in New York? Slightly more specific question. To answer it, we're going to need a slightly more complex model. So one way that you can think about these models is every model, all models are wrong, but some are useful, and they can be useful for answering these specific questions that you have. One last note before I let you go is something that we have not talked about much at all recently, but is absolutely essential that you keep in mind, is a lesson from Data 8. And that is, don't forget about standard errors. So if we go to think about Plato's allegory of the cave, these are all statistics that we've estimated here, 2.9 and 1.8. These are not the parameters themselves. These are based on the data that we have, the scant amount of data, these shadows cast upon the wall, and it's imprecise. And as a result, we should express that uncertainty that we have in these estimates that we've made. We can do that in terms of standard errors for each of these different thetas that we're estimating. There are several methods that you can use to get these standard errors, including the one that you saw in Data 8, that idea of bootstrapping the scatter plot, of resampling with replacement many scatter plots or 3D scatter plots, fitting many lines or many planes, and then looking at the distribution of those different coefficients. That can give you a sense of their standard errors.